In this video, we will be discussing the Cauchy's integral theorem. Before we move on to the theorem, we will be discussing some simple terminologies. The first one is a simple closed path. A closed path is a path whose initial and terminal points are the same. That is, if we begin at a given point, we will come back to the same point. Such a path is called a closed path. That is, its starting point and end point will be the same. If we start from anywhere in the path, we will come back to the same point again. Now, a simple closed path is a path that does not intersect itself. Okay, any path that looks like this is not simple. Any path, like for example, a circle, is a simple closed path. In the figure that you can see here, the first path is simple. The first path, it does not intersect itself, so it is simple. The second path here, again, it does not intersect itself, so it is a simple closed path. The third path is in the shape of an 8. It intersects itself at this point, so it is not a simple path. The fourth path that you see here intersects itself at two different points, so that is also not a simple closed path. Now we will discuss what we mean by a simply connected domain. In simple terms, a simply connected domain is a domain without any holes in them. Okay, as an example, suppose if you just take a circle like this, okay, if you just consider a circle like this, the interior of the circle, this is a simply connected domain because it does not have any holes. Now if I consider a ring shaped region like this, okay, the region between two concentric circles, then this is not a simply connected domain because this region here is left out. But the actual definition is a little bit more. The definition is a simply connected domain capital D in the complex plane is a domain such that every simple closed path in D encloses only points of D. Okay, for example, if you take the first example that we discussed, a circle like this, if you consider the interior of the circle, and if I take any simple closed path here, the interior of that path contains points from this domain D only. Okay, so it is a simply connected domain. But if you consider an annular region like this, that is the region between two concentric circles, and if I draw a simple closed path like this, the problem is in the interior of this path there are points which outside of our region. Okay, the region between this region was outside of our domain. Okay, so that is the precise definition, but we will not be needing that precise definition. The only thing that we have to consider is whether our region has any holes or not. So the first region that you can see here in our figure, this is a simply connected domain because it does not have any hole in it. This again, although it looks like it has two holes, but this is not part of the domain. This is the boundary of the domain. So again, it does not have any holes in it, so it is simply connected. The third figure that you see here is like an annular region, so this region is not part of our domain. Okay, so this is not a simply connected domain because there is a hole in our domain. Again, this domain that you see here, there are two holes, that is again not simply connected. This domain here is actually called doubly connected. There are two non-intersecting boundaries for that region. Okay, it is doubly connected. This region that you see here is called a triply connected. If there is one hole, it is called doubly connected. If there are two holes, it is called triply connected, and it goes on like that. Now we will discuss the Cauchy's integral theorem. The statement is like this: if f of z is analytic in a simply connected domain capital D, then for every simple closed path capital C in D, integral over c f of z dz is equal to 0. I'll illustrate the theorem using this figure. Suppose this region, the dotted line that you see here, that is our domain D. Okay, the interior of that is our domain capital D, this whole region. Okay, and I am having a closed path, simple closed path C inside of my domain. And if suppose I am having a function f which is analytic in this domain D, then integral over C f of z dz is equal to 0. I'll repeat again. If we have an analytic function in a simply connected domain D, then integral over any closed path, that is integral over C f of z dz, will be equal to 0. This holds good only for analytic functions. Okay, it can be restated like this also. Suppose I am having a function f of z. Suppose I am having a function f of z. I am having a closed curve C like this, and suppose f of z is analytic inside this closed curve C. Suppose f of z is analytic inside this closed curve C, then integral over C f of z dz is equal to 0. I'll repeat again. Suppose if I'm having a closed curve C, and suppose my function f of z is analytic inside this closed curve capital C, then integral over C f of z dz is equal to 0. Okay. Now, a simple closed path is sometimes called a contour, and an integral over such a path a contour integral. Okay, I'll repeat. In such a case, that is whenever we are integrating over a closed path C, then our function, then the integral is called a contour integral. That is the integral, the path, if the path is a closed path, then that integral is called a contour integral. Now we'll use this theorem on some examples. Consider some functions like this: e raised to z, cos z, z raised to n, etc. The speciality of these functions is that, suppose you consider e raised to z. E raised to z is analytic in the entire complex plane. Suppose you consider the complex plane, there is no point on the complex plane where the exponential, where the function e raised to z is not analytic. At every point the function is analytic. Okay, so such functions which are analytic in the entire complex plane are called entire functions. That is, they are analytic everywhere, analytic for all z. There is no point where f of z is not analytic. Such functions are called entire functions. Examples are e raised to z, cos z, z raised to n, etc. So for such functions, integral over c e raised to z dz is 0 for any closed path C. Okay, that is, you consider any closed path C in the complex plane, integral over c e raised to z dz will be 0 because it is an entire function. Similarly for cos z, so you consider any closed path in the complex plane, integral over c cos z dz will be equal to 0. Similarly for sin z raised to n, z raised to n is also an entire function, so you consider any closed path in the complex plane, integral over c z raised to n dz will be equal to 0. Now we will consider some functions where the points where the functions are not analytic is outside of our contour. Okay, so we'll see what happens when the points where f of z is not analytic are outside the contour. Consider this function sec z, integral over c sec z dz. We are going to integrate sec z over the unit circle. Okay, so if you consider this function sec z is 1 by cos z, so it is not analytic whenever the denominator becomes 0. That is, whenever cos z becomes 0, the function will not be analytic. So when is cos z 0? Cos z, you know, the curve is something like this. Okay, it goes on like this on both sides. So at pi by 2 it is not 0, at 3 pi by 2 it is not 0, at 5 pi by 2 it is not 0, etc. It goes on like that on the right side. On the left side, at minus pi by 2 it is not 0, then again at minus 3 pi by 2 it is not 0, and it goes on to the left also. So to sum it up, z, it is cos z is equal to 0 whenever z is plus or minus pi by 2, plus or minus 3 pi by 2, etc. So sec z is not analytic whenever z is plus or minus pi by 2, plus or minus 3 pi by 2, etc. But the region where we are trying to integrate is the unit circle mod z equal to 1. So this is the unit circle. You can see this figure here. This is the unit circle mod z equal to 1. And plus pi by 2, 3 pi by 2, 5 pi by 2, etc. All those points are outside of our region. Similarly, minus pi by 2, minus 3 pi by 2, minus 5 pi by 2, all those points are also outside of our region. Now, this function sec z is analytic inside this unit circle. So integral over c sec z dz is equal to 0. That is our result. Even though sec is not analytic everywhere, we are only trying to integrate sec z over the unit circle, and inside the unit circle, that is inside mod z equal to 1, the sec z is analytic. So integral over sec z dz, integral over mod z equal to 1, sec z dz is equal to 0. Now let's consider another example. Integral over c dz by z square plus 4, where c is the unit circle, mod z equal to 1. Again, z square plus 4 equal to 0 means z square equal to minus 4 or z equal to plus or minus 2y. Now if you consider the unit circle, plus or minus 2y, both plus 2y and minus 2y, both these points are outside of our region. Okay, so this is our region, that is in which we are trying to integrate. Integral over c mod z equal to 1. Now both the points where the function is not analytic are outside of our region. So, or in other words, the function is analytic inside mod z equal to 1. So integral over c dz by z square plus 4 is equal to 0, because inside mod z equal to 1 the function is analytic. You just have to consider the points where the function is not analytic or the function is not defined in that terms. Okay, so z 1 by z square plus 4 is not defined whenever z square plus 4 is equal to 0. It is not analytic whenever z square plus 4 equal to 0 or z equal to plus or minus 2y. But these points are outside of our region, so the function is analytic. Now, this is if a function is analytic inside a given curve, then integral over c f of z dz is equal to 0. But it does not mean that that should be the only case. The function can be 0 otherwise also. For example, integral over c dz by z square is equal to 0. This we have studied in the previous video. Integral over integral z minus a whole raised to m dz is 0 whenever m is not equal to minus 1. That result we have already studied. So integral over c dz by z square is equal to 0 whenever c is mod z equal to 1. But that does not mean that the function is analytic. Okay, so even if the function is not analytic, sometimes the integral may become 0. And the second thing is simple connectedness is essential for this result. Okay, so for that you just consider this ring shaped region, that is the region between these two circles. Consider the region between these two circles. Then if suppose I am having a function which is analytic in this ring shaped region or in this annular region, can I use the Cauchy's integral theorem? No, I cannot use Cauchy's integral theorem, because this is not a simply connected domain. Okay, because there is a hole in this region, so I cannot conclude that. If suppose I consider this red shaped curve that you see, I cannot say integral over c f of z dz is equal to 0. I can, maybe it is 0, but I cannot use the Cauchy's integral theorem to state that it is equal to 0. Okay, the Cauchy's integral theorem cannot be used here because the region is not simply connected. Now the next result is, so using this Cauchy's integral theorem, we can actually state that if a function is analytic inside a given domain, then it is independent of path. That is, if f of z is analytic in a simply connected domain capital D, then the integral of f of z is independent of path in D. Okay, so it is proof is simple. If you want, you just listen for some time here. Suppose if you are having some sort of a domain D like this, okay, and I want to state that it is independent of path, and I am having a function f of z which is analytic in this domain D. Okay, suppose I'm having a point z0, suppose I'm having another point z1, and suppose I'm considering two paths. Okay, so the first path here is say c1, the second path here is c2. Integral over c1 f of z dz will be equal to integral over c2 f of z dz. Okay, it will be integral independent of path if the function is analytic in this domain. Actually, you can use this Cauchy's integral theorem to prove that, because this, if I take, that is this path c1 and minus c2, if I take this whole path here, c1, that is I'm starting from here and I'm coming back to here, so I'm traveling along c1 and I'm traveling along opposite in the opposite direction of c2. This path, this is a closed path, so integral over that path c, I'm going to call that path c, is integral over c is equal to 0. Now integral over c, I can actually write it as integral over c1 plus integral over the opposite direction c2. Opposite direction I'm just calling minus c2, which is equal to integral over c1 minus integral over c2. Now this is equal to 0, so integral over c1 is equal to integral over c2. The proof is not relevant. The only thing that you have to understand is, if a function f of z is analytic in a simply connected domain D, then it is independent of path. Now, Cauchy's integral theorem for multiply connected domains. Okay, that is, suppose you are having concentric circles like this. This is, say, a circle C1, this is, say, the circle C2, and suppose if I'm having a function f of z which is analytic in the region between C1 and C2, then integral over C1 is equal to integral over C2. That is what this theorem states. That is, for doubly connected domain D with outer boundary curve C1 and inner boundary curve C2, if a function f of z is analytic in D, integral over C1 f of z dz is equal to integral over C2 f of z dz, both integrals being taken in the counterclockwise direction or both in the clockwise direction. That is, if C1, this curve C1 is in the anticlockwise direction, C2 also should be traveled in the anticlockwise direction. If I am taking C1 in the clockwise direction, C2 should also be taken in the clockwise direction. That is the only restriction. Okay, so if for a ring shaped region like this, integral over C1 is equal to integral over C2. Now this can actually be taken up for many holes also. Okay, for example, for multiply connected domains like this, suppose if I am having a curve C like this, suppose if I am having three curves C1, C2, C3, okay, and suppose if it is, if I'm having a function which is analytic in the region bounded between C and all these curves, this interior of C1, C2, C3 is not included. If f of z is analytic in the region bounded by C and C1, C2, C3, then integral over C1 C is equal to integral over C1 plus integral over C2 plus integral over C3. Of course, integral over f of z dz, I'm not filling it up, f of z dz is equal to integral over C1 f of z dz plus integral over C2 f of z dz plus integral over C3 f of z dz. Here also you are having f of z dz. Okay, this is called Cauchy's integral theorem for multiply connected domains. Thank you.